Hi, I'm Tim Miller from the Computational Health Informatics program at Boston Children's Hospital and Harvard Medical School. And today I'm going to be talking about the smart Cumulus Text-to-FHIR NLP pipeline. I'm excited to be here at FHIR DevDays and looking forward to seeing the rest of the conference. So first I'll introduce myself. My name is Tim Miller. I'm the PI of the Machine Learning for Medical Language Lab. And we're inside of the Computational Health Informatics program, also called CHIP, at Boston Children's Hospital, and I'm also an assistant professor of pediatrics at Harvard Medical School. In my lab, we build algorithms that help machines understand how to read health-related texts. So sometimes that's electronic health record texts, sometimes that's social media texts having to do with health, and sometimes that's things like biomedical journal articles. In general, our approach uses machine learning. We do a lot of deep neural networks for text understanding. We work on information extraction, all sorts of interesting problems to try to better understand the meaning in the text of health-related texts so that we can use them for downstream purposes. Another member of my team, Ben Mao, is going to be talking for part of this presentation as well. So he did a lot of the important implementation work on this, and we sort of worked together on the design along with several other people. So he'll be speaking later. He's the lead developer at Boston Children's Hospital. So first, I'd like to give a little bit of background on what natural language processing is. So the context is, we know that unstructured text represents a large chunk of the important information in electronic health records. So when you have electronic health record systems, there's the sort of structured part that uses a lot of coded data models, things like billing codes, ICD codes, things like procedure codes, CPT codes, and all other sorts of, checkboxes and drop-down menus and things like that, where you're selecting from a coded set of possible replies. And those are the types of things that are sort of easy to put in databases, easy to query over. Of course, there's always going to be problems moving from one system to another. I know that's a whole big thing, but at least, from within a system, it's sort of simple to figure out what was the value of this coded variable at this time. It's in a row in a database somewhere, and you can query that database the way we're all used to using SQL. Natural language, on the other hand, has this complexity where for any given thing that you might be talking about, there's a lot of different ways of talking about it. So it's ambiguous and difficult to compute over as a result. So for example, the expression rheumatoid arthritis can be referred to several ways just by that phrase, rheumatoid arthritis. Some people will write it RA, some people might write it rheum arth, and so on. There's a lot of different ways to discuss it. And that's one of the main use cases for NLP in healthcare, is basically making the unstructured part of the electronic health record look like the structured part. So we put in a blob of text with no sort of deep structure. NLP figures out what is going on in this blob of text, and then puts it into what looks more like a database that you can query over using codes. And so the types of things that we might want to get out of unstructured text are things like disease diagnoses, signs and symptoms, and procedures. There's also, you can imagine medications, anatomical sites. But then even going beyond the sort of concept level, there's this idea of relations between elements. So we are interested in doing semantic relations like location of. If we have a disease mentioned, but we also have an anatomical site mentioned somewhere else in the note, we want to know, are these two things linked? Is this disease present in this anatomical site specifically, or is it just a coincidence that they happen to be nearby each other? Another relation is severity of. If you have a disease or a sign symptom, and then you have a severity modifier like severe, moderate, mild, we want to know, is this modifying this sign and symptom over here, or maybe this disease disorder over here? So this is another thing that NLP can get us, and of course we can structure this as well once we understand this. We can have the link be between two structured coded concepts. Another type of relation that's really important is a temporal relation. If you have an event like in a disease, sign symptom happening for a finite time period, temporal relations can help us figure out where to map this sign symptom on the timeline, from say before the patient came in to sort of right in the middle of their inpatient visit when we prescribed some medication and the symptom stopped, for example. And so all in all, this is just a way of saying unstructured data has really deep and potentially finer grained information than structured data alone. And for that reason, I think a lot of people who are interested in doing research on electronic health records are really excited about the potential of extracting information from unstructured text to be able to do research on it. So existing NLP software for electronic health record text, there's a few different open source tools. There are several sort of closed source tools or hybrid tools or sort of software as a service type tools. But we're really interested for this project on open source tools so that the work we do can be contributed back to the community and potentially gain a lot of users and maybe potentially become a project of its own where people would feedback onto that. So as a starting point to use open source tools for this project, there's a few different ones that we thought of. One is Apache cTAKES. And so this is a project that was started at Mayo Clinic, but is now primarily developed at Boston Children's Hospital where I worked, and it's a project of the Apache Software Foundation. So it gets the infrastructure from there. It has a lot of users across the world. Another one is MetaMap, and MetaMap is less of a general purpose tool. It's more of a very specific tool of mapping concepts or mapping strings to concepts. And so this is released by the National Library of Medicine. And then there's a recently released tool called MedSpacey, which is quite nice. It's based on the Spacey Python toolkit, and this is being developed by a group at University of Utah. And so we spent a bit of time on that as well. And despite this sort of ecosystem of tools, open source, closed source, and everything in between, it's been hard for us to find FHIR-based tools or FHIR tools that are sort of already FHIR enabled. So there's a couple exceptions to that, and one is cTAKES-FHIR. So there's a sort of starting point for a module in cTAKES that's called cTAKES-FHIR, and basically this takes the cTAKES output, which is in a data structure, and sort of converts it into a FHIR data structure. So we looked at this to see if this was a good starting point for us, and we found that basically they're doing mapping into resource types that we think are not specific enough for the use cases. And so we thought we would probably want to make some modifications to that. There's another tool called NLP-to-FHIR, which was developed by the group at Mayo Clinic. And what they've done is basically wrap several different NLP open source components, including cTAKES, but also including MedXN and MedTager, which are some medication information extractors. And then they did a lot of mapping from the output of cTAKES and these other systems into FHIR resources. So what we found with that is that their mapping aligned with sort of what we thought was a sort of logical way to do the mapping, but they didn't do as deep of a job filling in the sort of the structures in the resource. So we wanted to sort of take that as a starting point. What are the mappings from semantic types into FHIR resources, and then go deeper on that, add in additional information to the FHIR resource. And so this project, the NLP part of this project, sits inside of a bigger project, the goal of which is to leverage the sort of upcoming FHIR Bulk Data Export API to build a sort of pipeline solution that lets you pull from a FHIR Bulk Data Export, process structured data through some pipeline, process unstructured data through another pipeline, remerge them, and then put them into a FHIR Analytics DB. And that way, once you have that Analytics DB, you can use apps that hit that database to sort of answer different questions, or you can have a SQL interface for power users who want to run sort of data science type queries. And so this project that I'm talking about here is essentially what's in this box as NLP transform. So there's a lot of detail that goes into it, but that's just how it fits into the bigger picture. Another piece we wanted to develop for this project is COVID-specific terminology. So a lot of the mileage we're going to get out of NLP systems is mapping from strings and unstructured text to sort of standardized concepts and terminologies. So, there are common terminologies like SNOMED and RxNorm that sort of take the space of medical concepts and assign all the different possible concepts in the real world to entries in these terminologies. But of course, since these terminologies are released once every 6 months or once every year sometimes, they're not always up to date. And so COVID-19 was a great use case in terms of seeing, like, if you want to extract COVID-19 related terminology, how are you going to do it with existing NLP systems? And so what we did was we took a couple of publicly released terminologies that different people in the community had shared. So one of them is from David Hanauer at University of Michigan. So he made this freely available. Another one is called COVOC, which is from the Swiss Institute of Bioinformatics text binding group. And this looked to be kind of a crowdsourced effort where they shared a Google Doc and a bunch of people were adding terms to it. So I took those two terminologies and then I combined it with SNOMED CT and RxNorm default dictionaries and cTAKES, which would give us a sort of general medical coverage. And then I created a sort of Uber dictionary that had all these concepts built together. So you can do both COVID-19 specific terminology and general medical terminology. So using that extended terminology, I was able to create a cTAKES container. This is a Docker container that wraps the built-in cTAKES REST server. And so my modification was basically the container piece of it and the terminology piece of it, where I created a new cTAKES pipeline that uses our terminology, and then I put a Docker wrapper around it, and then I start up the REST server inside the container. And then what you can do is just hit that Docker container at port 8080 with a string at a certain URL, and then it'll send you back a JSON blob in a sort of ad hoc format that was native to the cTAKES REST server. And then from there, the idea is to transform that into FHIR. So at this point, I'll pass it over to Bin Mao, who's going to do the rest of the presentation.
We are taking the JSON output from cTAKES NLP process and transform them into standard FHIR resources. Based on the semantic type of NLP contents, these following mappings has been used. Disease and disorder goes to condition resource. Sign and symptoms goes to observation resource. Procedures naturally goes to procedure resource. And we also assign medication to the medication statement resource. The concept codes are stored in resource.code.coding, except for the medication statement, it is stored in medication codable concept. You may find proof of concept code in the link below. We store both the code from original ontology and UMLS CUI code. As you can see the example below, we have 2 SNOMED code and 1 CUI code. Also in the same node, we use extension to indicate the location of the text within original document. In the future, we also need to keep the unique document ID just for the reference. We came across a couple issues along the way. One specifically needs mentioning is how to represent the negated values. Unlike coded data, text data are frequently mentioning things that are not happening. We have a few proposed solutions. One of them is to utilize modify extension, but this approach may not be compatible with all the systems. Some systems are not designed to handle the modify extension. We can also use resource-specific tag. For example, procedure will have a status undone. It may not give us the precise text meaning if the text says not recommended. Also, there are some thoughts about putting the negated concept into observations. If you have better ideas, please don't hesitate to reach out. For the next step, we want to have some improvement on the performance. First is the scalability. Since this process is mainly designed for bulk data process, we need to figure out how to process millions of nodes in the reasonable time frame. Also, we would like to add some features such as temporality and semantic relations. Last but not least, we want to have some analytics optimization. The goal is to improve the query performance against NLP data.
So to conclude, we've built a containerized solution for mapping from electronic health record text to FHIR. We had to solve a number of challenges along the way. We have some challenges that we still think we need to do better at in order to make the system even handle more use cases. But the source code for what we've done is available at the following repos. And of course, we know this community has a lot of combined wisdom, so we're happy to take feedback and advice from anybody who has ideas on how to push this thing even further. So if you want to contact me, you can find me on the speakers gallery, or you can email me here or tweet at me at tmills. And I just wanted to acknowledge the funding from the ONC and HL7. Thank you.
Hello, everybody. I hope you can hear me okay. Thanks for coming to the session, and I'll be here for till the end of the hour if there are questions, or you can contact me via email if there are additional questions. But
Have you guys, I'm just curious, Tim, have you looked at the product that Amazon offers, Amazon Web Services, to process,
comprehend.
Yeah.
Yeah, and Ben did a deeper look than I did, so I don't want to say anything out of turn. But my two takeaways from that were, so I presented a system at one of the AMIA conferences last year where I did a cost analysis of how our EC2 based system worked, and I had put a number in there just for people to see what it was, and just to be transparent. And then someone just happened to tell me, oh, that's way cheaper than Amazon Comprehend. so I can't vouch for that myself, but that's just what somebody told me when I put our numbers out. And then the second thing was I believe they have even a version that writes some kind of, quote unquote FHIR. And we looked into that a little bit, and our takeaway was they're kind of taking the output and sort of cramming it into FHIR. But not sort of mapping it into FHIR, if the distinction makes sense. So that it might be sort of readable as FHIR, but you would have to sort of still learn their entire data representation model in order to do any querying. So that was I don't know, there might be some people from Amazon on the call who might disagree with me, but that was that was our impression when we looked at it several months ago.
Okay.
The other thing is, of course, Amazon is no harm in it. They're a for-profit company. What we're trying to do is build an open source product that a lot of people can use.
Tim, this is Sadhana Alangar, HL7's Director of Education.
Different purpose, right.
There are a couple of questions in the question box. Do you want to take those?
Sorry, I must be missing it. And
I can read those for you.
Sure, that'd be great, yeah.
The first one is, what are the repo addresses again? That was so good.
Oh yeah, so I can share. I have the have it right here. I can bring those up at the end. There we go. Can everybody see those?
Yes, we can.
All right.
And do you want to take up the second question?
Sure.
You mentioned some issues around negotiation. How does your solution handle the numerous ways? Negation. You mentioned some issues around negation. How does your solution handle the numerous ways that negation may be expressed in medical notes?
Yeah, I mean, that's a great question. But just to be clear, there are sort of two components to the negation issue. The first is, can you properly detect negation? That's like an NLP question. And then the second thing is, how do you represent negation in FHIR? And so this, what we're complaining about here is the second issue. The first issue is also really hard. It's not a trivial problem. I would say it's not a solved NLP task, but we do have built into cTAKES several different modules that are with the goal of detecting negation. And so one of these is a rule-based system called NegEx, or Context is a sort of more modern version of it. Context, it's called. If you want to find the citation, the first author is Harkema, Harkema. And that's a rule-based system that's fairly easy to implement, that has a dictionary of negation keywords. You give it the concept that you want to classify, and it has a couple of rules that it applies. Like, does it have this keyword within so many words of the entity you're trying to apply? We also have machine learning models that are trained on sort of data sets that try to figure out where we've annotated existing cases of negation, and so those methods are on some data sets a little better than the rule-based one, but are a little slower to run. So the system that I've described today used the rule-based one just for speed purposes, but we're still figuring out how to represent it in FHIR. We have negation extracted in cTAKES, and we think the accuracy is probably in the range of like 80 to 90%.
Okay.
Next question.
Any other questions? We just have 2 more minutes.
I mean, I could follow up my question.
Sure.
What data sets are you using for the NLP training?
For negation specifically, or?
Well, I mean, yeah, for negation or just for anything. I don't know if are those like openly available data sets, or are there stuff you guys call from the hospitals you guys work at?
Yeah, so most of the data sets we use were ones that were created either for the community to share, in which case they're not, they're not sort of like freely available, like you can't download it like Wikipedia, but they usually have some sort of access, controlled access via data use agreements. And so several of those come from the I2B2, and now it's called N2C2 shared task data sets. That's where we get some of our negation data. We did have a project a while ago called SHARP that that's where we trained the negation system mostly. That data was never made publicly available, unfortunately. But the I2B2 does have a publicly available negation data set. And then some of the other component systems inside of cTAKES are trained on data that is de-identified, but I don't believe was released.
And have you made efforts to look at different domains within the larger medical domain? Like different specialties may have different ways of expressing negation in medical notes, right? Like it's crazy. Yep. Like I've looked at this problem. That's the only reason I'm asking these questions.
No, yeah, we've looked at that extensively. I have an NLM grant dedicated to the idea of domain adaptation, where we actually spent quite a bit of effort on negation specifically.
Cool.
And so we had a paper at BioNLP maybe 4 or 5 years ago where we looked at how bad, a paper in +1 5 years ago where we looked at how bad this problem was. And that's where we showed that the rule-based systems do not port well to different data sets.
Yeah.
And then we built a machine learning system using support vector machines and feature engineering. In the meantime, we've built neural network-based systems using BERT. And we published at BioNLP and in Jamia subsequent works on our negation systems and how well they do in different domains. So in total, we have access to 4 data sets where every time we publish, we say, not just here, we optimize for this one data set and we got 90%, but we show we're working on this task of always trying to do it in the way that adapts to new domains. But that's a really exciting area. Hopefully we can do it on every NLP task and not just negation.
Tim, this has been an awesome presentation, but I'm afraid we have to let you go.
All right.
I hope you'll be able to answer any further questions in the Q&A section on Whova, and encourage everyone to ask their questions there so that you can get back to them. Have a good day.
Yeah, thanks a lot. Please do feel free to reach out to me. Thanks a lot.